Okay. Main thing to note is there's no class on Friday. We're running the state physics meet. Let's see if I can get rid of mine. It'll be over in the center. So there won't be any class.
Okay, there we go.
If you happen to be here at Tarleton, then you'll get to meet the physics conference. And for those people who are not, then you are. I want to pick up, I'm not going to go through, I said, the rest of the stuff. I put it all in your notes. I do want to look at the results, and I sent you out a set of questions. And those questions, how I got those questions is they came off of old exams. So, for obvious reasons, they would be good ones to be able to solve. So, looking at some of the results that come out of the mathematics after you work through all this stuff, these were important fundamental things that you would be expected to know off your head, and they will not be put on a quiz sheet or anything else. The first one is that they often, when people give you stuff in problems, they don't use the quantum numbers. And the reason they don't use the quantum numbers in describing the states of the hydrogen atom is that the chemists, well, physicists actually at the time, but chemistry and physics in the 1900s were kind of all together. All right, and so at that time, what they did, they were looking at spectral lines. And so as they looked at the spectral lines, they named things based on the way the lines look. So for instance, if something was a fine line, then they gave those states the letter F for fine. And if they were really bright, they gave them P for principal. And if they were really sharp, they called them S for sharp. So they were based upon the way they looked. They didn't have quantum mechanics at the time. Well, it turns out that the shapes of those are directly related to quantum states' angular momentum numbers. So the S lines happen to all have an angular momentum quantum number of L equals 0. So people can say things like, this is a 3S state. You got to figure out what quantum numbers you get out of the 3S. Yes, I'm getting a hand waving from Preview. Did you have a question? Okay, so because you get this 3S, that means that you need to be able to figure out what those quantum numbers. The S tells you that the L number is 0. So they didn't say L equals 0, but they told it to you because they told you it was 3S. Another big thing that you need to know is that you know the quantum wave number. There are 3 numbers you have to be given. You have to be given N, L, and M. The principal quantum number, the orbital quantum number, and the magnetic quantum number. The N and the L tell you what the radial quantum state is. And the L and the M tell you what the spherical harmonic are. So if you have those 2, you can find the wave function. Now, I'm going to give you on the test, as I did last time, some information that you need to be able to work with. So you've been given the spherical Laplacian, so I can ask you to work on deriving things from that. You've been given how to find the Legendre associated polynomial, because I gave you this formula that will let you calculate it for whatever L and M I give you. And if you know that, you can plug it in here and you can find the spherical harmonic. So that's the theta and p part of the hydrogen wave function that I've given you. And I can generate for anyone. I can give you a table and give you 2 or 3, but this gives you all of them. Okay? I've given you the radial part on the back page. So with the radial part and with the front page where I can get the angular part, that means you have the wave function. So make sure that you can take what you're given and be able to find those. Now, the other thing you need to become proficient with over time is you need to become proficient with using this book. There are a lot of different math handbooks, but you're not going to work problems that are like x squared plus 3 equal 5. If you are, that's basically technician work. You should go to DeVry. All right? These type of problems are more complicated, and the functions that come out of them are more complicated. And the information that people have obtained is in this book. So you need to be able to use this book. So for instance, you have something on associated Legendre polynomials. If you go in this thing, you have Bessel functions. You have things on the Legendre polynomials. You go to the next page. You actually have tables of elliptic integral solutions, which you'll find useful in courses like math methods. You have the differential equations themselves. For instance, there's whole sections here on Laguerre and associated Laguerre polynomials. That's the hydrogen wave function. It doesn't say these are the hydrogen wave functions, but there they are. There's the Legendre and associated Legendre. It doesn't say these are the angular momentum solutions for quantum mechanics, but they are, because they can be used in other fields. So all the information you need to know, far more than what's in my table, is in this book, but it's of no use if you don't know how to use this book. So you need to get where you become really good friends with your math handbook. All right? So for instance, it says associated Legendre functions are on page 162. If I go to 162, I've got things like, there's Legendre's differential equation. That wasn't the one that we had. We had the associated equation. And it tells you that that's your differential equation. Those are your solutions. And in fact, they've even worked out a bunch of them for you. So if I've got a differential equation, I can put it in this form, then I've got the answer in the book. But not if I don't know how to use the book. Okay? Likewise, there are things called generating functions often that can help generate all the others. And there are properties of these things. For instance, these have this unique property I'm going to talk a little bit more about. That if you multiply two of these functions together, and then you integrate it over all possible angles theta, if these two functions are the same, the answer is 1. But if those two functions are different, the integral is 0. That's a great savings than sticking in a whole bunch of sines and cosines and having to do all sorts of really hard integrals. If you know the answer is either 1 or 0, and that's all you have to do. So these things act like unit vectors, like ijk. And this integral acts like a dot product. If they're aligned, the answer is 1. And if they're not aligned, the answer is 0. So they're said to be orthonormal. If they're at right angles, their normal is 0. And if they're aligned, then it's 1. So they're normalized. So they get to be 1 if they're dot product together. And if they're perpendicular, if they're orthogonal, the answer is 0. So they form bases. They're independent. Something else it tells you. If you were to integrate this guy right here, it turns out he's not normalized yet. He gets you this number. Well, that would be the square of the normalization constant. So 1 over that square rooted would normalize these guys. So again, I don't have to do those hard integrals. Only if I read this book and understand this book. So, you don't have to use the Shams. You can use any math handbook you want. I suggest get one handbook. It could be the CRC. It could be the REA handbook. Get one of them. Use only that one. And get where you know it, like front and back. What do I like, Shams? CRC is like $100. If you want the leather bound, it's like almost $250. If in REA, it's about $65. This thing's under $20. And if you look around at half-price books, I've gotten it for as low as $2. And at the university down there, I picked one up for $1. So I like the price. And it's good enough to do anything you need for undergraduate school. I suggest getting this one, but the only reason I like this one is the cost. Downside of it is paperback. I go through these things like water. Okay, so I've gone through like 5 of them since I've been here. But every 2 years, the cover comes off and falling apart. I have to buy new. But get you one. All right. Like I said, oh, by the way, there's your Riemann polynomials. So there's my harmonic oscillator solution. All right. right? Everything you need to know. One thing, 6 functions, side functions, elliptical intervals. Get to know this book. In addition, of course, it has integration. So it's got 48 transforms, Laplace transforms, system and signals class. Highly useful for that class. Series, how to do vector analysis, Cal 3. Make sure you learn your book. Really useful. All right. Some other things. So besides knowing these special functions in the book, here's some results that we know. The energy, we know the energy of the problem. The energy for these problems are all minus 13.6 electron volts divided by n squared. They depend only upon the principal quantum number n. That's because we've assumed there is a single point charge at the nucleus and only one electron. If there's more than one electron, let's say you had a proton there and an electron here. Right now, the force is straight along the radius. And you have a central Coulombic potential, 1 over r. You get this answer. That's what's worked out. But if you had 2 electrons, say there's an electron over here, then that electron would apply a force that repelled that electron. And it's not at the origin, so that means the sum of these forces is no longer along the radius. When that happens, this thing then will no longer just depend on n. For that reason, the 2s orbit and the 2p orbit do not have the same energy levels, which you don't get out of the hydrogen atom solution. So the reason that chemistry fills up the way it does is because they don't have exactly this 1 over r dependence. You have to account for these other forces. Now, we're not going to deal with that in this course, all right? That's why they do. You take a chemistry class, an advanced quantum class in chemistry, or you do a more advanced physics course, they'll deal with that. But we're not going to. We're just going to leave it with the 2 electrons by themselves and treat them kind of like we did with the Bohr atom. A hydrogen any type solution. Now, because of that, it says I can change L to be any value I want. So if n was 2, L could be 1 or 0. And those are different states. They have the same energy. So therefore, it's got a degeneracy for different values of L. And likewise, I can change n, because if L is 1, n could be minus 1, 0, or 1. Those are different states. They have the same energy. So it has M degeneracy. So there are a bunch of electrons, if you had a single atom and ignore their electron-electron effects, they would all have the same energy value, have the same energy level. The M are produced because it's a spherical type problem. And the L only occurs if it's 1 over r. So in nuclear physics, it's not 1 over r. And you can get, in fact, different energy levels, and you can have more values of L than just n minus 1. All of that stuff is specific to this equation. So when you change and put the nuclear force, you can have a 1f orbit. Not allowed in atomic physics. Totally allowed in nuclear physics. And it can have a higher energy than a 2s orbit because of these so-called coupling effects. Another important thing is we've got formulas for the angular momentum and the z component of the angular momentum that you should know. We'll use these equations a lot. This one says that if you give me the orbital angular quantum number and you add 1 to it, multiply those two together and take the square root, multiply by h bar, you get L. Notice this is not in h bar. So Bohr gives the wrong answer in deriving the Bohr atom. He used completely the wrong angular momentum. And in fact, everything about Bohr's atom is wrong, except the energy. So the Bohr atom gives the correct energy, but he gives a lot of wrong stuff. So the Bohr atom is wrong. Chemistry idea these guys go around in circles is wrong. But we use it when we want to find energy because it's a whole lot easier than doing all this math. Unless, of course, you just like spherical functions and you like doing, Laguerre-associated polynomials, okay? You like solving three-dimensional differential equations. That's why people still use the 4F. You don't need the math. But it only gives the correct answer for the energy and for a knot. You're going to find it's the most probable location, not the only location in the electron. Those guys are the main things to know in that chapter. So with them, I'm going to do some problems. You're given a 2p electron, and you're asked a set of questions about the 2p electron. First question they might ask you is, what's the principal quantum number for this problem? Anybody? What's the principal quantum number for a 2p electron? I got a 2, I got a 1. Which one is it? Huh? It's the 2. Then they ask, what's the orbital angular quantum number? How do you know that? Because it's P, that's right. So you know L is 1. Then they ask you, what's the magnetic quantum number? Now, did they tell you up here what the quantum number was?
It's electrons.
Sorry?
It has a certain number because it's an electron.
It has a certain number because it's an electron, but they did not in any way tell you which state in the P that it is. Now, they can do that. Once you get to spin, they can tell you how the L and M sub L and the stuff does. They didn't tell you any of that. So this M sub L can have a value from minus L and then increase by single units till it gets to L. 0, 1, that's L, that stops. So, in the 2s, there are 3 states. Sorry, the 2p. One of them is for the ML equal minus 1, one of them is for the ML equal 0, and one of them is for the ML equal 1 state. And what we find in the next section is there are 2 states in each one of those, and those are due to another quantum number called spin. So there can be a spin up, there can be a spin down. Up and a down, and up and a down. How many total electrons can I put in there? 6. That fills it. In the 2s, get a 2s, then you'd only have ML equals 0 because L is 0. So it goes up by 1 from 0 to 0. It's minus 0 is still 0. So you can only put 2 here. So how many total can you put in the second orbit? 8. Go back to the first orbit, you can only put in 2. So 2 and 8 is 10. The next thing up there in those so-called noble gases is 10, and that is neon. So the Schrödinger equation completely describes and explains all of chemistry. There's no sort of funky monkey business about, well, you sort of kind of put them in this order, or we're going to move them around like this. It explains it all from first principles. All of chemistry is nothing more than solving the Schrödinger equation. Give me a computer, give me the right functions, and I said write a code, and I can do any type of chemistry, solid state physics, or electrical engineering you want. Describe any device, whether I've ever seen it before or not. All I got to do is work this equation. This equation is everything in quantum world that Newton's law is. It solves everything. Newton's law does all civil engineering. The Schrödinger equation does all solid-state electrical engineering. All of your study of materials is completely contained inside you. And you either know it or you don't know it. You don't know it, you don't know anything. You know it, you know everything. The problem is solving it. It ain't trivial to solve. It's a differential equation. It can be quite complex. Energy. Here's my answer to that one. Okay, so energy, I'm looking for the second state, is minus 13.6 electron volts over 2 squared. So you get a calculator and punch that. Let's see. It'd be like minus 3.4, I think. And they all have the same state. There were no electron-electron corrections. Every one of these states would be the same. And so the electron would just as likely want to go into this state as the 2s state, and that's not what happens. That's because when you add extra electrons, they begin to talk to each other, and depending on how close they are to each other, or how much time they spend near each other, they're going to put more or less corrections to these guys. So these guys are going to get shifted. There are some other reasons for that, besides just the electric force. There are also magnetic forces involved, and we'll come to that in the next chapter. Magnitude of the angular momentum. H bar square root of L times L plus 1. So the question is, do you know L? The answer is you do know L, because we already found it. So it was 1 times 1 plus 1. So that's the amount of angular momentum. And that's not the same thing as 2h bar, like Bohr would have said. Bohr got it wrong. The z component of the angular momentum. Well, that depends on our little m sub L here. Sometimes they put the subscript L and sometimes they leave it off. The main thing is to know it's not mass. It's a quantum number. And the second is it does depend on the value of L because it limits what you have. But when you start getting really complicated equations, you got so many of these m sub L's, it just becomes a hassle and they just start leaving it off. But always remember, it does depend on L. Now, I can't tell you this because they're different values. So therefore, there are different values that the z component would have. So it might be minus h bar. That would be if m sub L was minus 1. Or it could be 0. Or it could be h bar. So the total angular momentum of the system, because you think of it going around, and since it goes around, it has a certain amount of angular momentum. Okay, we know amount, but we don't know exactly the amount for the x and y components, and I can't tell you the z components, and it can differ. So what does that mean? Well, usually what people like to do is they like to draw some sort of a picture. So they'll draw you a picture something like this. And this is the z-axis. And they'll come out here and they'll say, okay, well, you have this, that's L, and that's the square root of 2h bar. That's how long it is. And if you were to draw that kind of like a sphere, and if it was down here, I didn't kind of get my sphere right, it'd be like that. And it still would be square root of 2h bar. And it also might come down, straight down to like here. What I know is this is minus h bar. So that is minus h bar, and that's the length. This is the way it's pointing in space. How can you get something like that? You remember the kind of right-hand rule? If you have something that kind of goes around, if you have something that goes around like that, you wrap your fingers around it, your thumb points in the direction of the angular momentum. So if it's doing that, it's like this. But you can tilt that in all sorts of different ways. So for instance, you could have it going like and then it would be over here. So depending on how these orbits are tilted, will tilt this angular momentum area. This guy up here would be H bar, and this would be the one right along here, would be the one that has no component along the z-axis. Now they look like arrows. Be a little careful about this. These are not arrows in the sense that I know the x and the y components. I cannot know the x and the y component. So they're really kind of cones. It could be anywhere around that circle, tracing out kind of a cone. Or it could be up here, tracing out a cone. Or it could be here, in which case it's tracing out a circle. It could be anywhere in that circle. I cannot know where. And in fact, if you attempt to measure it, you'll get a value. But if you then try to measure the z component again, it'll change. Because if you measure any of these other components, it'll then start going around, if you want to think about it like that, around that newton. You cannot know all three components. It is impossible to have total precision of the knowledge of the angular momentum. If you did that, then you had to know the linear momentum. Right? L is equal to R cross P, so you'd have to know P. And you'd also have to have perfect precision and knowledge of position. You can't know those. That violates the uncertainty principle. So this is another example of an uncertainty. There is a limit to what you can know in quantum mechanics. You can know how much is along the z. You can know the total, but you can't know the x and y components. You can know the total, and you can know the x component, but then you can't know the y or z components. You can't know more than one component of angular momentum and the total. That's it. So, since you can only know one, we by default find whichever one you know as a z. That's the direction we're going to put it. Now, that is shown to you in detail in your book. On page 272, where he's worked through all these cones. Okay? And where he's talked about all these particle components. So that's figure 8.7. He's got a much nicer drawing than I have. Isn't that good? Make sure you understand it. This is a weird thing. There's nothing like it in classical physics. It says that if you try to think, it can either be here, it can be there, it can be there. But how the hell does it get from here to here if it can never exist in between there? The answer is, it doesn't go between there. It goes pop, pop. They got a name for this. They call it spatial quantization. Very weird thing. And what people will ask you sometimes to do is to give them this angle here, theta. So for this problem, there are only three possible values of theta. You can have this theta, you can have 90 degrees, or pi over 2, or you can have the theta that goes all the way around to here. Now, why that's going to be important is that this L is also connected back to the magnetic field of this system. So by putting a magnet, I can measure different energies. That means this actually is a way of storing information. I could use this, for instance, as a computing capability if I want. Or I can see these effects in various spectroscopies. So we know this happens. You don't get a continuous set of lines. You have a very specific set of lines based upon this L. I'll leave you to read how to find that angle. It's simple trigonometry for your book. All right, so much for that one. Next set of questions. All right, next set of questions are more complicated. Those are the easy ones. Those are just play and shove. Those are the ones, by the way, that are on high school exams, the district and region. So obviously this will be a little bit harder problem. This one says, you have a 1s electron, and I want to know its most probable location. So what makes this harder is that now I really have to deal with wave function. I'm not just plugging in quantum numbers anymore. I actually have to really do calculus and know what I'm doing. So that brought in three other things to talk about. We talked about number 6, you may only know one component of the angular momentum. We've already used some of these properties. It's this property here. Radial probability distribution function. So I remind you that the integral across all space of the wave function squared is equal to 1. What's different here, so this would be over all space, is what type of integrals you're doing. So for instance, back in X, Y, and Z land, it looked like this. It went from minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. We were integrating over dx, then we were integrating over dy, and then we maybe integrated over dz. So you found the wave function, you squared the wave function, as you multiply by its complex conjugate. And then you had integrated over all the possible values of x, all the possible values of y, and all the possible values of z. But we're not in this Cartesian land anymore. We're back like we were with the Boltzmann distribution in spherical land. So, spherical land, we talked about earlier this semester, you've got something here with a theta and an r. So if you want to talk about changing space, you can change this some distance, that's dr. You can rotate this vector like this, as r d theta. And then you've got to look at the projector. I'll bring that down here. There's phi. That's r sine theta. Same as right here. It's the opposite side of the triangle. And then as you move phi, you're going to take this point and you're going to move it like that. So you're getting a side up here. That side is r sine theta d phi. So there's the three sides of your cube. So my volume is dr, r d theta, r sine theta, d phi. So it's r squared dr sine theta d theta and a d phi. So let's put that back up in here. I got 1. Now I'm going to integrate r, and r goes from 0 to infinity. And I'm going to integrate phi. This is going to go from 0 to 2 pi. I'm going to integrate theta. It's going to go from 0, that's when it points straight up, to when it points all the way down. That's pi. Still have my phi squared here. But now I got to put this thing in. So I got an r squared, then I got a sine theta, then I got a d theta, d phi, dr. And that's the interval you're going to have to be constantly dealing with. Okay, so you're constantly got the integrating of these spherical coordinates, not over Cartesian coordinates. So you have to get used to doing that. This shows up a lot in physics. And unfortunately, these intervals can be hard, so there's some tricks that we've put in order to make the intervals easier for us. One of the things that we notice is, I really don't like heavy trig functions in here like this. Because trig functions tend to mean I need a lot of trig identities, and that makes life hard. So, one of the things that you noticed I did in the notes was I said, hey, look, define a new variable x. It's the cosine of theta. Take its derivative. Derivative of the cosine is minus sine theta d theta. Okay, that almost looks like that whole thing there. I'll just put a minus sign here, make that a plus. And now I can get rid of this with a new variable dx. So if I do that, I get 1 is the integral. I got this r stuff. And I'm going to have this phi. But I have this new, and this is going to be an x. And I'm going to have del my phi squared, r squared. This, I'm going to replace that with dx. And I got a minus sign. Now what can you do to these limits here if you have a minus sign? You get rid of the minus sign.
Flip them.
Flip them. So if you put in 0 for the cosine of theta, you put 0 in for theta, cosine of 0 is, and so the 1 would be down here, but I'm going to use the minus to flip it. So I'm going to put the 1 up here. And then I'm going to put the pi into the cosine. Cosine of pi is? Negative 1. But instead of being on the top, because I put the minus sign in, it goes on the bottom. So if I can replace all the cosines in this phi with x's, and all the cosine squares with x squares, oh, there might be some sine functions in there. Okay, well, hold it. Cosine squared theta, it would be x squared. Sine squared theta. Sine squared theta, that's 1 minus cosine squared theta. I can replace every trig function with a bunch of polynomials, and I can integrate polynomials from -1 to 1, and that's a hell of a lot easier to do. This shows up in every spherical geometry type problem you'll ever run into. In E&M, in mechanics, in quantum, everywhere. Get used to working with spheres. It's one of the 3 basic shapes people build. All right? And it makes these problems a lot simpler if you will change this. So that's why the Legendre function is always written in terms of x in the math handbook, and not in terms of cosine theta. But you have to remember that the x is cosine theta. Because you're going to want to do this anyway. You're going to want to turn it into x. So having it in x is a good thing. A whole lot better than having it in terms of theta. The other neat thing about these guys, these phi functions, you said, turn out to have a very unique shape. They have an r, and then they have this y function. These guys here are the only ones that have any theta and phi in them. And this part here has nothing but r. So that means we can break this up into 2 parts. We can break this into a part that deals with theta and phi. That's going to deal with the y. And we can break this problem up with the r. So I can take this r squared and that dr, and I can plug it over here by itself. So I can make it 2 simpler integrals to mess with. Now, if I do that, here's what I get. Phi star times phi. That's the square of phi that I'm always looking for. So this is going to give me this. And it's going to give me this. Now, if you want to write that as the absolute value of y, go ahead. I'm not going to for another reason, but it would be perfectly fine to put that just like you do here, with an absolute value value. And I'm going to take that, and I'm going to plug that into here. So I'm going to get this looking thing. So that's one set of an integral I have to work. And I'm on the other side, I'm going to have this one. So this is the radial part. And this is the angular part. And you can take a problem like this anytime and do this. So for instance, if you integrate that over all space, like it shows, it will be 1. You didn't care about where in the radius. If you had a sphere, and you're going to look at any R you want, if you just look all over the thing, if you have something flying out, it's eventually going to go through the sphere. If you have a sphere like this, you got a bunch of stuff flying out, it eventually passes through the sphere. By the way, if you make the sphere even bigger, how many ever pass through there? First one will eventually pass to the second one. The area may get bigger. It does, 4 pi r squared. But all the stuff, all the light will still go through. They call these angles the solid angle. And it's measured by taking the total area and dividing by r squared. The total solid angle is called 4 pi. That's where you get 4 pi r squared. So if it's this, the area is 4 pi times this r. If it's out here, the area is 4 pi times its new r squared. The angular part always gives you 4 pi. Consequently, some books will just write this like this. Just make that over this. They won't write those individually. What they're saying is go all the way around the circle and you will have covered the entire 4 pi steradians of the solid angle. I'll leave that for you to go and look at your math handbook. You are going to hit it a bunch through your career. The sooner you learn it, the better. If you do it overall, it's 1. What if these two my's weren't the same function? It'd be 0. So if you gave me a 2s state and a 2p state, because the s and p are not the same, they don't have the same L, this interval will be 0. Guaranteed. If in fact you gave me the same p, but there were different m states, it would be 0. Automatically. No need to do the integral, no need to look it up. If I can write it in terms of these y's, it does the integral for me. The only possibilities are 0 and 1. What a great savings versus you trying to figure out how to take something with a lot of, I don't have one of these, where is it? Just a second. Take this and multiply by that and integrate it over all the possible angles. You just take this integral, you multiply by that, and then you integrate it over all space and find the answer. The answer is 0. There's no need to do that. I'm guaranteed it's 0. You don't know that, you get to do all the cross multiplying and then do all the integrals in the math handbook. And when you get done in about 2 hours, you come up with 0 if you do it right. So knowing these spherical harmonics is a tremendous time saver. If you don't know these properties, you're not going to be able to keep up with your homework in future courses. So get to be a good friend of these guys. They're important. That's why we invented them. They're really helpful. If I can take a function I don't even know, if I can figure out how to write it in terms of one of these guys, like 5 times this, then if I know the other part is any of the others, it's 0. And if I know it's the same as this, then the answer is 5. And I don't have to do the integral at all, I need the integral table. These functions for spherical problems reign supreme. They are every bit as important as sines and cosines are in regular trig land. Okay, so learn to know them well. You'll get plenty more chances to deal with it in an E&M class and with math methods and doing all sorts of stuff. They're important, so learn them. All right. So, my problem. My problem was to find in B, I didn't want to do B first. Where did we do B? I thought I had A. I lost my problem. So what is the most probable location? So I need to get that probability function. And it turns out because you can integrate anywhere, all over space, in the theta and phi, that integral is going to be 1. So the only part I have to worry about for this problem is what's going on in R. So this part right here is called the radial probability distribution. So P is R squared times R in L squared. And that problem, again, is put in your book. So if you look in your book, in chapter 8, he has a formula. .44. Find the probability as a function. Find the probability as a function of R. Take R squared, multiply with the radial part of the wave function squared, and that will give you the probability. What I've been asked is, when is this the maximum? How do I find that? Well, I got this on the table. I need to remember I got to multiply by R squared. If I don't do that, I'm going to mess this up. Okay? So let's see. P is R squared. R in this setting was the 1s. What's the 1, 0 squared function? I look on my table. And there's the 1, 0 wave function. Radial part. I need to square that. So this is 3/2, so I square that, that'll be cubed. This is 2, I need to square that, it becomes 4. This is E, if I square it, it becomes minus 2 R over A naught. So I take that and I write that up here. R squared, 1 over A naught cubed, 4, E to the minus 2 R over A naught. There's my probability distribution. Now you can attack this problem as it is, but you'll make your math harder. So let me tell you another trick. Meters is what R is in. That is a terrible unit for atoms. They're nowhere near a meter. They're about the size of the hydrogen atom. They're close to A naught. So let's work in units of A naught. So what I'm going to do is I'm going to make a new unit of distance, which is in units of A naught. And I'm going to call it rho. So if R is A naught, then rho is 1. Or if R is 2 A naught, then rho is 2. So we're talking about sizes of atoms. It's called often a reduced length. So I'm going to rewrite my function here. I'm going to take that r squared, I'm going to put it in here. I'm going to take out an a naught. There's r over a naught squared. So I still got an r squared. And I have an a naught squared, there's that. And I need one more because I had a cube, so I need one more a naught, there it is. I have a 4. I have an e to the minus 2 r a naught. And actually, heck, I tell you what, I see a 2 up there. I'm just going to make this 2 here. I'm going to make it that instead. I'll change it. So if I do that, I can just take this guy out and put him in here. Just algebra. So that's 1 over a naught. That's rho squared. That's e to the minus rho. Zero. I need to make the derivative of that wave function, or that probability, 0, in order to find the maximum. You have a function, you want to find its maximum or minimum, you take the derivative, put it 0. So, I take the derivative of this function. Okay, so 1 over a naught. Take the derivative of that, I'll get 2 rho. Take the derivative of this, I get e to the minus rho minus 1. So 0 is, I can factor out a rho. I can factor out an e to the minus rho. And I get 2 minus rho. One possibility is rho equals 0. That means you're at the nucleus. That's no probability. One is rho is infinity. That means you're at infinitely far out. There's no electron there. So the answer is rho equal 2, which is 2r over a naught. So r is a naught. The Bohr radius is the most probable location for finding the electron. See if you can't work the rest of those problems, and I'll see you guys on Monday.